In my previous videos, I talked about the interactions between different particles. There, I said which particles attract and repel other particles. But one thing I didn't say was how to find the force between those particles. In the real world, the force between two stationary bodies with charge, which is the electrostatic force, is given by Coulomb's law. Here Q1 and Q2 are the charge of the bodies, R is the distance between them, and K is a constant. If the two bodies' charges have the same sign, the force is positive and they repel each other, and if the bodies' charges have different signs, the force is negative and attracts the two bodies. Note that this only applies to point or spherically symmetric charges, and not other things like two infinite plates or the blue and yellow shells. The main difference between electromagnetism in real life and in BFDI is that in real life, charge is a real number, but in BFDI, charge can't be represented by a single real number, since there are multiple types of charge, which we see in the interactions between atomic particles. We need n real numbers, where n is the number of different types of charges that exist, all interacting in different ways with each other. A way to model this is using linear algebra. If you don't know linear algebra, the essence of linear algebra series by Dribble and Brown is a good place to learn. Just keep in mind that here, the vectors represent charge instead of points, with each coordinate on the vector corresponding to one type of charge. The constant k is replaced by the matrix k, which encodes the interactions between charges. Each entry of K is a sum of forces using the convention I introduced last episode. These sums are scaled by the distance between the two charges raised to some power. So, for example, one of the entries of K can be this. With this, the formula for the electrostatic force is this. As an example, if we have these 2 point charges separated by a distance of 2 and K is this, the force applied on A is 2 units of force of order 1, 4 units of force of order 2, and 1.5 units of force of order 3. Another thing we can do with linear algebra is a change of bases. The meaning of changing the basis is to change the units used. I think the most useful unit system for charge is one where each particle has its own dimension, but it could be useful to have some other system instead, and we can use a change of basis to convert between the two. Now, you might be thinking, but what are the elements of K? But the only way to determine those values is to see the movement of two particles with charges, and this isn't shown in the series, so we can't really know those values exactly. But I can give the sign of some of those values if the basis vectors of the matrix are the atomic particles I described in my previous videos. A positive value means that the particles repel each other. A negative value means that the particles attract each other, and 0 means that there is no interaction between the particles. One thing that you may notice about this matrix is that it is symmetric along the diagonal. This means that the output of K doesn't change if you swap the terms around. However, this doesn't have to be true. If K isn't symmetric, the force between two particles doesn't have to be symmetric. This goes against Newton's third law, but I don't think that there is any reason for this law to be true in BFDI. If the matrix isn't symmetric, the electrostatic force formula will give the force applied to the body with charge Q1. Another important concept in electromagnetism is the electric field. The main feature of the electric field is that force at some point equals the electric field at that point times charge. In the real world, since charge is a real number and force is a 3D vector, since there are three spatial dimensions, the electric field is a 3D vector field. But what about in BFDI? In BFDI 6, there is this scene.
Eraser. The number of votes you got is the factorial of the difference of the square of the number of spatial dimensions in this universe and one more than the smallest perfect number.
And that is
9. You're eliminated. Haha. If you were smart, you'd know the result is actually 2. I guess you're not so smart after all.
grrr.
Knowing that 6 is the smallest perfect number, we can solve for the number of dimensions and we get that the answer is 3. This means that force is also a 3D vector and charge is an ND vector, where n is the number of different charge types. This means that the electric field is a 3 by n matrix field. If we consider one charge, we can multiply the electric field by charge to get a force field, which is a vector field. If instead we only know the charge vector up to scale, we have an infinite family of vectors, but we can still have a 3D vector field. First, choose one of the vectors from that family and call it Q1. Then you calculate what I call the adjusted electric field, represented with A, by multiplying the electric field by Q1. Then, to find the force for some charge Q, first find a number K such that Q equals K times Q1, and then the force is A times K. In summary, in BFDI, there are multiple types of charges, which can be represented as a vector, and we can use this formula to get the force that a point charge Q2 applies to another point charge Q1. And the electric field is a 3 by n matrix field where n is a number of different charge types. If we only want to consider a single dimension of charges, we can use the adjusted electric field for that charge, and then we only have a vector field instead of a matrix field. This is all I have for this video. Goodbye.